Welcome to Chapter 4 of our Data Communication and Computer Networking course. In this chapter, we will explore the local area network and wide area network technologies. This session 1, where we will focus on the LAN connecting devices, the hardware that unifies multiple segment structure into efficient networks. We will examine the TCP/IP layer classification of these devices, and then dive deep into repeaters, hubs, bridges, and internet switches, understanding their functions, advantage, limitation, and operational characteristics. Let us begin by understanding why connecting devices are essential. LAN do not naturally operate in strict isolation. For business processes, segments must dynamically connect with other networks or the global internet. To build these connections, we leverage specialized interconnecting devices. These hardware devices function on distinctly different operational layers of the TCP/IP stack. At the top, gateways operate at the application and transport layers, processing ports and protocol IDs. Routers and layer 3 switches operate at the network layer, processing logical IP addressing. Bridges and layer 2 switches operate at the data link layer, processing physical MAC addresses. And repeaters and hubs operate at the physical layer, processing only bit-level signals without any address intelligence. Understanding of this classification is fundamental to design efficient networks. Now let us examine repeaters, the simplest of all connecting devices. Electrical signals travel along copper wires, suffer from attenuation, degrade their original integrity over distance. A repeater intercepts physical signals, actively regenerates them, and passes them on at a bit level. It functions exclusively at the physical layer of the OSI and TCP/IP reference suite. However, there are latency boundaries to consider. To preserve essential collision detection mechanisms in half-duplex Ethernet, no more than 4 repeaters may safely sit between any 2 hosts. Exceeding these boundaries delay collision propagation, triggering errors. The advantage of repeaters are clear. They are highly direct signals boosters that extend maximum physical distance restrictions cheaply, and they are cost-effective due to very simple circuitry components. However, they have significant disadvantages. They have zero logical filtering capability and propagate noise alongside genuine data streams, and they cannot isolate collision domains. Next, let we explore hub, which connects multiple network nodes to a single physical device, acting as a central point of collisions. Hubs are fundamentally multi-port repeaters that transform a linear bus layout into a star topology. Any packet arriving at the port is instantly broadcasting or copied out to all other connected ports. Hubs become into varieties: passive and active. Passive hubs are simple physical connection point requiring zero external electrical power and do not amplify signals, functioning entirely between the physical layer. The active hubs utilize integrated electronics to clean and amplify signals, working as multi-port repeaters within the active signal boosting that require continuous power. Enterprise intelligent hubs offer sophisticated remote monitoring and control operations. They come in stackable form, designed to mount sequentially on racks to save costly enterprise servers, closet floor spaces. They support remote SNMP, allowing networking engineering teams to remotely monitor and diagnose ports. And they enable virtual LAN or VLAN logical support, allowing basic configurations for software-driven virtual logical networks. Now let us move on to the bridge. which logically isolates separate network segments. Working at layer 2, they make parsing-driven decisions. Bridges read and parse the physical source and destination medium access control or MAC address and frames. They isolate local traffic and filter out noise, protecting joining segments upon frame arrival. The bridge queries its database against the destination MAC to choose one of the three actions. The first is filter or drop, which occurs when the host is mapped to the same incoming ports, dropping the frame safely and isolating the segment. The second is forward, when the host is mapped to a different port, providing targeted delivery to the specific output port. The third is flood, which occurs when the MAC address is currently unknown, sending replies to all active ports. The bridge learns throughout a process. It boosts with an MPT mapping table database, then reads the source MAC of incoming frames and maps to that port. This enables targeted delivery for future packets without broad flooding. However, bridges face a critical problem, the bridge loop problem. Deploying a parallel redundant bridge blocks a single point of failure but introduces critical risks if left unmanaged, including the broadcast storm with infinite frame replication between segment passes, memory bloat where MAC tables continually shift, mapping registries, crashing switches. The solution is the IEEE 02.1d spanning tree protocol or STP. The spanning tree algorithm resolves physical loops by dynamically calculating the logical tree layouts, setting redundant interfaces to blocking status to block active loops. The STP continually monitors segment link status for active failover management, and if primary links fail, blocking port to switch to forward automatically. Finally, let us examine Ethernet switches, which are high-performance multi-port bridges that provide a dedicated segment for every single port. Switches offer a collision domain isolation, where every port operates on its own dedicated collision domain. They use a silicon acceleration with built ASIC or ASIC chips, enabling hardware-level forwarding. Switches eliminate contention limits by providing zero congestion, meaning no bandwidth sharing occurs between distinct active switch ports, and they support full duplex simultaneous bidirectional transmissions. Switches operate into primary forwarding modes. The cut-through mode forwards the frame immediately upon parsing the destination MAC address, offering the lowest possible latency delay, but propagating the CRC frame errors. Store and forward mode buffers the entire incoming frame, validating the CRC integrity before transmission, filtering out malformed frame and adapting speeds between links. To summarize the first session, we have explored the key LAN connecting devices and their TCP/IP layer classification. Repeaters simply regenerate signals at the physical layer. Hubs are multi-port repeater that broadcast to all ports. Bridge filter and forward based on the MAC addresses at the data link layer, which spanning tree protocol resolves loop issues. And switches are high-performance multi-port bridges providing a dedicated collision domains and full duplex communications. In our next session, we will explore the wide area network topology and protocols. Thank you for watching, and I look forward to see you in the second session.